At the end of the last video, I was using an optical sensor to try to measure the RPMs of a DC motor. What I had done was put a cardboard disc onto the shaft of the DC motor with two slots cut out. And this should lead to two rising edges. So when the cardboard interrupts the optical sensor, I get 5 volts as the output, and when it's open, I get 0 volts. So this should lead to 2 rising edges and 2 falling edges during each cycle of the disc. But what was happening was I was getting 4 rising edges and 4 falling edges most of the time during one rotation. And all I could figure was this was due to the bouncing that can happen when you have a transition of a digital signal from 0 to 1 or 1 to 0, similar to what you get from a mechanical button. So I used the same type of circuit to debounce this, and that amounted to a pull-up resistor here, value of 10K, and then a resistor of 100 ohms and a 1 microfarad capacitor to provide low-pass filtering, and then a Schmidt trigger 74HC14 to provide some hysteresis and clean up the signal. And that seems to have worked. When the switch is closed for this circuit, R2 is in the circuit. So this is what we have when the switch is closed. And if we write the Kirchhoff's current law again, we can write this equation, which gives us these set of equations resulting in this differential equation. And when we go through all of this, we find that our solution is this equation. And now here is our time constant. Well, actually, this value right here is our time constant. So here's the circuit that I use to debounce the optical sensor. So here's my optical sensor input coming here, and that's attached to both a resistor here and a capacitor that provides low-pass filtering. This switch represents the opening and closing of the optical signal through the use of the cardboard disc, interrupting the optical value. There's an R1 here that is a pull-up resistor. Then after the low-pass filtering, the signal is fed into my Schmidt trigger, and it's there cleaned up a little bit, inverted, and then sent to my pin D2 of my Arduino, which is the hardware interrupt pin. So for this circuit, when this switch is open, R2 is out of the circuit, and we end up with this being our circuit for the case when the switch is open. And if we use Kirchhoff's current law, we can write the differential equation in this fashion. And when we solve this, we get our voltage is equal to this value right here. So we see that our time constant is R1C. Okay, so let's see how well things work here. I've got an RPM measuring device used for measuring the RPMs of propellers on RC airplanes. And I also have the circuit set up, and here's my motor. So I'm going to run my program now, and I'm going to run it at a value of 100 out of 255. And when I look at my program here, I am getting values of about 2100 RPMs. So let's see how that agrees or disagrees with what I get from my meter here. So it might be hard to see it on the screen. This is saying, let's back it off here far enough. saying about 2190, 2160. And I'm showing 2100 as measured by the screen. Let's try another value here, say 200 out of 255. Should be considerably higher RPM. And it is. It has changed to about 3300 or 3360 RPMs. So now let's see what we get from my meter here. And I'm getting about, settles down, 3360, 3480, 3390. So it's within pretty good agreement. Let's go all the way to the maximum value here, 255. And now I'm going to be reading 3900, 3960. So 3900 to 4000 RPMs. And I'm rating 4050, 3960. So this appears to be right on.